Okay, so this is the test. So let's see if this works or not. So I will, if we want to design an IIR filter, okay, there are several steps. So first, we want to find the analog template. Okay, in the week 1, I will put the link down below. We talked about this, right? So for different order, you have different template. For example, n equal to 1, you have this one, and for n equal to 2, you have s square root 2s plus 1. So for n equal to 3, you have a different one, something like this. Okay, for n equal to 3. So you can imagine that the transition for different order are different. Okay, so the higher order ones having a faster transition. Okay, so based on some criteria, then you can select what kind of filter you want. Okay, so if you have that, we're gonna do the second step, which is called a pre-wrap. Okay, so I'm gonna jump to number 3 first because it's more important. So it's called a denormalize. Okay, that's the key step. So we want to have the h hat s, okay, which is coming from the original HAS, the template, one of the template we got, and then we're gonna substitute s with something. Okay, with it's depending on which filter you want to have. For example, if you want to have this low pass filter, okay, then you replace s with s over omega hat p. Okay, then you're gonna ask, what is omega p hat? That is something called a pre-wrap. It's coming from the cutoff frequency or passing band frequency omega p here. Okay, so let's look at how the wrap thing works. So this omega passing band hat equals to tangent omega, so omega p, the passing band, over multiply t over 2. Okay, because let me change the color here. Sorry, I can't change it. Let me make it so. Okay, can't change the color. All right, here we go. So because omega p equals to 2 pi fp, okay, and t actually just equals to 1 over fs. Okay, this is about sampling frequency. This t is about sampling frequency. Okay, so we can change this one to a different form. So this one equals to tangent 2 pi fp, okay, over 2 fs. That'll be the same thing. Okay, so we have the first and second step, and this number 4. The fourth step is what we're going to do is this called apply a BZT. Okay, we're going to apply BZT. It's very easy. So you have this template, okay, from analog. All right, so you just replace this S with Z. z minus 1 over z plus 1. Then you got a capital HZ. All right, that's the full step you're gonna follow. All right, so after this, let's look at sorry, maybe move a little bit. Okay, so let's look at the first question. We have those requirements. Actually, we can use those to figure out how much is n. But this question actually simplified our job. The HAS already been given, so this one's tick. We already got the first step. And the second step is we want to know, it's a low pass filter, right? We want to know the cutoff frequency. So we know this frequency is 60 Hertz. We know that stop band is 85. Okay, so this actually cutoff frequency is 60. So we're gonna do pre-wrap. Okay, so we're gonna do pre-wrap, and we know that omega p hat equals to tangent 2 pi fp, and here this fp we know is 60 Hertz divided by 2 multiplied with fs 256. Okay, you plug in the numbers and you will find this equals to 0.906 something. Okay, we know this one, and we're gonna do the normalize. Okay, so that's was the second step, and the third step we want to do normalize. So we have this HA, the analog template hat, gonna equals to the original one, which is this one we have been given. That's the HAS. Okay, we're gonna put this HAS replace the S with that one. If you look at them, because it's low pass filter, with S over omega p hat. Okay, not that hard because we got everything. Then we just start to plug in. Then we have this S over omega hat p cubic plus 2 S over omega hat p square plus 2 S over omega p hat n plus 1, that 1 over it. Okay, just replace all the S with the S over omega p. Okay, then after you got this, the last step is easy. So the number 4, the last step, you have this one, then you replace this S with z minus 1 over z plus 1. Okay, if we have this omega p hat cubic on the top, so if we can put this one on top, cubic, okay, then we have this s cubic plus 2 s square multiplied with a p hat plus a 2s multiplies p hat square and plus a omega p hat cubic. Okay, then what we need to do is we're gonna plug in this number, s equals to z minus 1 over z plus 1. Okay, so the last step is hz, just gonna equals to, plug these in, the p cubic on the top, the bottom is plus 1 z plus 1. Okay, Okay, so you're gonna clear the term, move this upside down. So there are a lot of calculation need to be done. Then you can start to write the difference equation for that, because hz gonna equals to yz over, because that's the transfer function, right? So hz equals to yz over xz. So in this way, you can write that yn equals to bunch of xn, something like that. Okay. Yz. So you can write the difference equation like, let me cancel this part. So, oops. So you can have this yz equals to, you have this whole hz thing, right? So this yz equals to hz, which is the whole big thing, multiplied with xz. Okay, so I won't give you the full solution. You can see the final version in the solution. Okay.